Okay. Assalamu alaikum, everyone. I hope you've had a great week and I hope you're enjoying first year so far. My name is Rawad Turko. I'm a second year medical student, and today, inshallah, we'll be talking about the electrophysiology of the cell. So before we get started, I've asked around, I asked a few first years, and from what I gathered, I understand that this lecture might seem a bit daunting to a lot of you. It's very physiology heavy. There are some physiology lectures that are sort of like half physiology and half anatomy or half, something else. This one's very, very physiology. It's all about, chemical stuff and electrical stuff and diffusion and potential and membranes and things like that. It's very, very physiology heavy, but I want to assure you that you don't have to know every single minute detail from your very first study. So this lecture sort of serves as your foundation of knowledge, and you'll be building upon this knowledge and upon these concepts more and more as you move through the year. Okay, there's many more lectures that build on this concept. So if you don't understand everything from your very first study of this lecture, don't worry, you'll learn more about it, inshallah, as you move along through the year. So one thing I also want to note is that if you're watching this later on on YouTube, you might notice that I'm not asking too many questions or I'm not being as interactive. And that's, it's not because I'm a horrible tutor. It's actually because I am recording this lecture, privately. So it's not online. It's not live. It's recorded. So it's just going to be me talking to myself for, however long this takes, inshallah. So I hope it's useful. Let's get started. Bismillah. So these are the objectives that we're going to be covering today. First, we're going to be going into the chemical aspect of things and talking about concentrations and concentration gradients and which way the thing is moved depending on which solution is more concentrated, things like that. Then we're going to be getting to the electrical aspect of things and talking about the charges of those ions and which way those charges moves and what diffusion potential grants which movement of which charges and things like that. It's all electrical based. Then we're going to be going into the homeostatic function of both of those systems. Okay, so how does the body work? How does the body grant movement of ions, keeping both of those systems in mind, and which directions the ions move depending on what the gradient is, and so on and so forth. Then we're going to be going to the driving forces. Again, which way that the ions move, depending on which driving potential is greater, what the permeability or the conductance is like of those ions and things like that. Then we're going to be going into specific ions. So that's sodium, chloride, potassium, and things like that, and talking about which way those ions move usually, all right, in your resting state. Then, speaking of resting, we're going to be talking about the resting membrane potential. Okay, that's the voltage, or that's the charge that your cell membranes are typically at your resting state, and what ions contribute to the resting membrane potential, and how does your body maintain that resting membrane potential. Then we're going to be getting into the excitable tissue. So that's action potentials and things like that. Now, this specific objective, as I mentioned, it's not, we're not going to go too deep into this concept because, as I mentioned, you're going to be taking it later on, or maybe you've already taken it in your action potentials lecture, and you're inshallah going to be having another PAL session specifically for action potentials. Then we're going to be getting into everybody's favorite part of any medicine lecture ever, which is the clinical stuff. Okay, again, we're not going to be going too deep into it. We're just going to be touching upon it a little bit just to get you some deeper knowledge of the whole concept. And finally, we're going to be going through, just a couple of questions just to test your knowledge. Let's get started. So here I have two compartments, okay, the one on the left and the one on the right. Okay, right now I don't want you to get too busy thinking about which one's extracellular, which one's intracellular. Doesn't matter. Let's just two compartments, okay? The membrane, let's say that the membrane, the line that separates both of these compartments, it is permeable to these ions that you see, okay? These ions, the A's, I'm going to call them the A's, okay? They're able to move throughout, or like to and from each compartment, because the membrane is permeable to these compartments. The membrane is permeable to these ions. Now, the one on the left, we can easily tell, is a lot more concentrated than the one on the right. There's just more A's in this compartment than there are in this compartment. Okay. Now, based on what we know of basic physics and basic physiology, which way do we think that these A's will move from which compartment to which compartment? There's nobody here again, but what you're thinking is probably right. Yes, these A's will be moving from the compartment on the left to the compartment on the right. Again, This only happens if the membrane is permeable to these ions, to these A's. Okay, if they weren't permeable, obviously there will be no movement. This stays the way it is. Okay, and that's because obviously you need to have these channels, you need to have these ion channels that are able to permit movement of these A's to and from the compartments. So that's the chemical aspect of things. Very, very basic. I doubt that many of you have trouble understanding this concept. Inshallah, you're all following along so far. So again, across the membrane, separating two differently concentrated solutions. So like this, left and right, two differently concentrated solutions. The one on the left, obviously, more concentrated than the one on the right. There exists a chemical gradient. Okay, gradient basically means just a difference, a chemical difference. Okay, difference in concentration. Now, this chemical gradient grants movement of the ions from the solutions that are more concentrated, so the highly concentrated solution, to the low concentrated solution. So again, as we know in medicine, always things like to move from areas of higher concentration to areas of lower concentration. So here, if we have or a chemical gradient within these two compartments, we can say that these A's are going to move from the left to the right. Okay, again, only if the membrane is permeable to these A's. This is a very, very important concept because this is a very oversimplified diagram. Okay, when we're talking about your body and the cells, the intracellular fluid and the extracellular fluid, obviously, it's not just one ion. It's a variety of ions. The membrane is not permeable to all of those ions. Okay, we're going to be talking about just a few channels that permit transit or permit movement of a few ions, not all the ions. Okay, so although you might have a concentration gradient for all of the ions, we can only allow movement of some of them. Okay, so this ion we can say is able to move through these compartments because the membrane is permeable to it, but it's not permeable to all of the ions. Okay, very important concept. And I added a picture of a hose here just to get you guys to understand this concept a little bit more. So when you're using a hole, obviously you have the nozzle and you have the outside. Okay, when you press on the thing, right, and it shoots the water, that's because of the concentration gradient. Okay, there's a lot of pressure inside of this nozzle, and that's what pushes the water out when you press on the thing, and that's why there's such a strong movement of water outside of the hose. Now, electrical. Now let's get into the charges and the voltages and things like that. Okay, now this one is just a little bit more confusing, so I need you guys to pay attention just for a little bit. So let's just establish a couple of rules before we get into it. Let's say that the membrane is only permeable to the positive charges. Okay, so the ones on the left. Again, I know that I put just charges, so positive and negative, but I want you to remember that these are ions. Okay, these are charged ions, whether positively charged or negatively charged. They're ions and they're not just charges. Okay, but let's just say that this membrane is only permeable to the positively charged ions and not to the negatively charged ions. Okay, so in the same way here that we see a concentration gradient, because the one on the left is more concentrated than the one on the right, we could say here that there's an electrical gradient. Okay, because we have permeability of the membrane to the positive charges, we can say with full confidence that the positive charges will move from the left to the right. Only if the membrane is permeable to the ion, and in this case, it is permeable only to the positive ions and not to the negative ions. Okay, the negative ions, the negatively charged ions, will not be able to move from the right compartment to the left because the membrane is not permeable to them. It is permeable to the positively charged ions, and that's what we see here: the movement of the positively charged ions from the left compartment to the right compartment. So across the membrane separating two differently charged solutions, there exists an electrical gradient. Just in the same way that we have a chemical gradient here, we have an electrical gradient here. This electrical gradient grants movements of the ions, whether from the positively charged to the negative or vice versa, depending on what ion the membrane is permeable to. Okay, so there's a lot of channels in your cell membrane, and based on whether or not those channels are open or closed, that determines what ion is able to pass through the membrane at any given time. Okay, so in this case, we're going to say that it's only permeable to the positively charged ions. I hope you're all with me so far. So we have chemical and we have electrical. And both of those things contribute to the movement of ions. So when we're talking about the movement of ions to and from the extracellular fluid, we cannot talk just in terms of the chemical aspect or just the electrical aspect. We have to consider both of those aspects. Okay, and that's what contributes to the homeostatic function of the cells. This gradient, okay, we're going to take the electric gradient, or we're going to be taking the chemical gradient. We're going to be putting them together. We're going to call it the electrochemical gradient. Okay, and that's what grants movement of these ions from the extracellular fluid to the intracellular fluid, and so on and so forth, and vice versa. Story time. Now we're going to be putting both of them together, and we're going to be going through the sequence of events, and inshallah, that'll make you guys be able to understand it better. So now we have the A's that we saw from the concentrate, from the chemical aspect, and we have the positive charges that we saw in the electrical aspect. Okay, so let's just do a little bit of world building. So we have, again, two compartments. The one on the left is more concentrated than the one on the right, but again, there's there's the electrical aspect that you have to think of. So we have positively charged A's. Okay, we have positively charged A's on the left and positively charged A's on the right, and there's more of those positively charged A's on the left than there are on the right. So if we only consider the chemical aspect of things, let's just forget about those ions, those charges for a second. Let's just look at the A's. If we only consider the chemical aspect of things, we can be sure that the flow of ions will be from the left to the right, obviously, because it's the same thing we saw in the very first slide. Okay, it's the same thing we saw in the first slide. There's just more A's on the left than there are on the right. Okay, so the movement, if we're only considering the chemical function, the movement will be from the left to the right. Okay, I want you to note, again, as I mentioned, that this diagram is an oversimplification. Okay, in reality, there are also negative ions in both compartments, but we're considering the membrane here to only be permeable to these A's and not to any other ions. Okay, so very, very important. Please remember, there's also negative ions in both compartments, but we're only going to be looking at the A's right now because the membrane is only permeable to those A's. Okay, so again, more A's on the left than there are on the right, movement from left to right. Okay, obviously. Now, this is going to happen, and that's what the chemical aspect is. Now is when we consider the electrical aspect. Okay, so bear with me just for a second. So we have positive charges or positively charged ions that left the compartment on the left, and they went to the compartment on the right. Now, we said that there are negative ions in both compartments. Okay, if we're losing positively charged ions from the compartment that's on the left, and we're gaining those positively charged ions in the compartment that's on the right, and there's no movement of negative ions, that begins to form a negative charge on the compartment on the left. Okay, I'm going to repeat. So we have positively charged A's on the left and on the right. There's more of them on the left than there are on the right. That will mean that the A's will move from the left to the right down the chemical gradient. When this happens, we see that we start to see a negatively charged solution that's on the left compartment because we have no movement of negative ions. Since the negative ions are staying in their place, we can't see them, obviously, they're not in this diagram, but since the negative ions are staying in their place, okay, and we're losing positively charged ions, we can see that the solution is becoming a bit more negative than it was before the movement of those positively charged ions. So as the ions continue to move from one compartment to the other, an electrical gradient begins to form between both compartments. Since the positive charges are leaving the compartment on the left, it will become relatively negative. And this is important, relative to the compartment on the right. So the compartment on the right is more positive or less negative than the one on the left. Eventually, and this is important, eventually the voltage and diffusion potential exactly counterbalance the chemical gradients, and the movement of ions ceases in both compartments. This is the major concept of this first part that we're going to be talking about, okay? Since we have this electrical gradient that's forming, and we continue to lose these positive charges, eventually the electrical gradient will start saying, no, hold on, I don't want to lose any more positively charged ions because we're like this is too much of a gradient, right? I'm developing too much of a gradient. I'm becoming too positive. I need to hold on to some of these positively charged ions, okay? But in the meantime, the chemical aspect of things is saying, well, still, but I still have a concentration gradient. Like there's still a gradient, there's still a difference that I need to equalize between both of these compartments. So I need to keep going to the one on the right. But you start having the sort of opposite forces, because on one aspect, on one hand, the electrical gradient will be saying, hold on, I want to keep some of these positive charges. And on the other hand, the positive charges will be saying, but I need to equalize both of these compartments, and I need to equalize this concentration gradient. So once both of these forces are equal and opposite, all movement ceases. Okay, and that's what's so important about homeostasis. Homeostasis does not exactly mean equilibrium. Okay, because you notice that there's still a difference in charges, whether outside or inside of the cell. Okay, just because we have these ions that are trying to sort of equalize the concentration on both of these compartments, it doesn't mean that will happen, because you have opposing forces. You have the electrical gradient pulling one way, and you have the chemical gradient pulling the other way. And once they're equal and they're opposite, all movement of ions will cease throughout both of these compartments. I hope that makes sense so far. So let's put it all together. The body compartments are always in a chemical and electrical steady states. Okay, that does not mean that it's chemically equilibrium, that we are in a chemical equilibrium or in an electrical equilibrium, because that would imply that we have equal concentrations on both of these sides if we're talking chemically, and equal voltages on both of these sides if we're talking electrically. But that does not happen, because we're in a steady state where both of these charges are continuously balancing the other one out. Okay, so at an electrochemical equilibrium, so it's not an electric equilibrium or a chemical equilibrium, it's an electrochemical equilibrium. The chemical and electrical driving forces are equal and in opposite directions. So they'll both be pulling the opposite directions, and that's why we see no net movement of ions once that chemical equilibrium electrochemical equilibrium begins to form. So no more net diffusion of the ion occurs. The equilibrium potential is the voltage that's required to completely oppose the chemical driving forces of an ion at any given concentration. Okay, now, so you have this concentration gradient. You have this sort of this chemical gradient that's going to be pulling these A's from the left to the right. Okay, but I mentioned that there's an equal and opposing electrical force that's going to basically seize all movement of these ions once you get to that point. That electrical point where you start to see that electrical point that's equal and in an opposite direction, then the chemical point, that is called your equilibrium potential. Okay, that's the electrical charge basically that's needed to equalize both to reach electrochemical equilibrium and to sort of oppose completely the chemical driving forces. This equilibrium potential, is calculated through the Nernst equation. Now, Nernst equation, I know it's a bit much. It's too math. I probably guarantee that you won't be given a question in the final that's asking you to practically apply the Nernst equation. They're not going to give you a bunch of numbers and tell you figure out the equilibrium potential of this ion. Okay, it didn't happen for our year. And it didn't happen for any of the older years. So Nernst equation, all you have to know that it calculates the equilibrium potential of a permeable ion. When we're talking about all of this, every single thing I just talked about so far, it's only for permeable ions. So it calculates the equilibrium potential of a permeable ion at any given concentration difference across the cell membrane. Okay, and I added a little drawing here to show you that you have you have a weight that we're going to call the chemical driving force, and a weight that's called the electrical driving force, and they balance the other one out when you reach the electrochemical equilibrium. Now, the weight of the electrical ball, okay, that's your equilibrium potential. That's the force that's required, or the charge, the voltage required to completely and oppositely oppose the chemical driving force. Okay, so now we're going to be getting into obviously the driving forces. Okay, let's say right now your membrane as it is, it's charged a certain charge. Okay, That's called your membrane potential. Okay, right now at rest, your membrane has a specific charge. This charge, let's say, is negative 74 millivolts. Okay, and your equilibrium potential, I mentioned here, your Nernst equation will calculate the equilibrium potential. Let's keep talking about those A's. The equilibrium potential of these A's, let's say it's positive 20 millivolts. Okay, now because we have this concentration gradient again, the ions will move from the left to the right. This is not new. We've talked about it a lot. When this happens, what do you guys think will happen to the membrane potential? Okay, so it's negative. It's negative right now. It's negative 74 millivolts. Okay, and it's gaining, or the one on the right, the compartment on the right, it's gaining positive charges. What will happen when we see movement of A's from the left to the right to the membrane potential? It's going to go up. Okay, so the membrane potential is going to increase when you have movement of these A's. Okay, now the equilibrium potential I want to mention, it's a potential, it's a potential voltage. It's the one that's required. It's the voltage that's required to oppose fully the chemical gradient. Okay, that doesn't mean that it will change because it's a potential. It's a equilibrium potential at any given concentration of these A's. Okay, but when we see the movement of these A's, that's when we see an increase in our membrane potential because we're gaining positive charges, obviously. So the driving force of an ion is the difference between the actual membrane potential and the ion's equilibrium potential. An ion is always trying to bring the membrane potential closer to its equilibrium potential, right? The magnitude of the current flow is determined by the size of the driving force and the permeability of the ion. So let's just talk about what that means for a second. So since our equilibrium potential is 20, it's positive 20, and we said that things are always trying to reach equilibrium. Okay, in this case, the electrochemical equilibrium, right? The electrochemical equilibrium for A is positive 20. That will mean that it's going to try to bring the membrane potential up to its equilibrium potential. Okay, so all the ions, any permeable ion will always be trying to bring or to pull the membrane potential towards its equilibrium potential. Okay, so if I had, for example, let's just give sort of a silly example. Let's say that my equilibrium potential is negative 1,000. Okay, very, very silly, very dramatic, I know. Negative 1,000. And there's still positive charges. Will we see the A's moving from the left to the right or the right to the left? I know you can't answer, but it's from the right to the left this time. Why? Because the membrane potential, because it's more positive than my equilibrium potential, which again, I said we're going to consider it negative 1,000. Okay, we're going to be losing positive charges in order to bring the membrane potential down to the equilibrium potential. In this case, it just so happens that it's positive 20, which means that we see an influx. An influx means an inward movement of the ions, an influx of these A's in order to bring up the membrane potential up to the equilibrium potential of ion A. Okay, so I hope that makes sense so far. I added a picture of a door here to show you guys the driving force. So when you have a closed door, right, sort of like a half closed door, and there's a lot of pressure on one side, like let's say there's a lot of people that are piling up behind this door to get to the other side, right? That basically tells you a lot about the driving force. So the magnitude of the current flow is determined by the size of the driving force and the permeability of the ions. So the more open the door is, the more people are able to pass through. The more closed it is, the less people that are going to be able to pass through. That's basically the entire concept of the permeability of the ion. Okay, so the more permeable it is, the higher the magnitude of the current flow is. Okay, that makes sense. Now let's talk about the specific solutes. Okay, now finally we can start adding some names to these compartments. Let's call the one on the left your extracellular fluid or your extracellular compartment, and the one on the right your intracellular compartment. Now, let's take a look at the concentrations at rest, usually, of these solutes. Okay, so sodium, for example, your very first one, there's 142 milli-equilibrium per liter. Just remember the number, 142. And on the inside, it's 10. Okay, so which one is more concentrated? Obviously, your extracellular compartment is more concentrated when it comes to sodium than your intracellular compartment. Okay, so when the membrane is permeable to sodium, which way will sodium move? From extracellular to intracellular, or intracellular to extracellular? Extracellular to intracellular, because again, things like to move from higher concentration to lower concentration. So sodium will move from out to in. Okay, so there's going to be an influx of sodium. Now, potassium. Potassium is pretty much the opposite. 140 in and 4 out. Okay, so more concentration in your intracellular fluid than in your extracellular fluid. Okay, so which way will potassium move? From in to out, the opposite direction. Yes. What about chloride? 103 out, 4 in. Left to right. And finally, proteins. Okay, proteins are not an ion, but they are negatively charged, so we could also consider them. Proteins on the intracellular fluid, they're 16, and extracellularly, they are 2. So they'll be moving inwards, out, this way. Okay. Now, one way to remember it is to remember that the P's are always moving out. Everything else is moving in. Okay. By the way, in your slides, you'll notice that there's actually a lot more ions, but these are the ones that were circled, and these are the only ones that they're going to ask about in your final exam anyway. So you probably don't need to bother to look at all the other ions. The only one I might say is a little bit important is maybe calcium, but again, you don't need to know it for this specific lecture. So for right now, only focus on these 4. So one way to remember the movement of these ions is to remember that the P's are going out. P's being potassium and proteins. So potassium is going out, proteins are going out. Everything else, sodium and chloride, moves in. So remember, salt, you can remember salt moves in, salt because NaCl, sodium chloride, salt moves in, P's go out. Okay, so Na and or sodium and chloride move in, and potassium and the proteins move out. Okay, these top 2, sodium and potassium, these are the ones that we want to focus on the most for the next section, which is obviously our resting membrane potential, and the contributions. Okay, so we're going to be talking about specifically sodium and potassium. Okay, so do you guys remember the Nernst equation, right? The Nernst equation, which tells you the equilibrium potential of a permeable ion. Okay, so it calculates the equilibrium potential of a permeable ion at any given concentration difference across the cell membrane. Okay, so every single permeable ion has a Nernst, or has an equilibrium potential. Okay, let's talk about the ones for sodium and potassium. Okay, so at rest, given these concentrations, which are 142 and 10 and 4 and 140, okay, the equilibrium potential for sodium is positive 61, and the one for potassium is negative 94 millivolts. Okay, now if you want to go, you don't need to dig too deep into what these numbers specifically mean. I just want you, because they're only for our case, in the case of this lecture, they're only important when we're talking also about the membrane potential. Okay, so I just want you to remember the numbers as they are. Positive 61 for sodium, negative 94 for potassium. Okay, you don't really need to remember like the specific number, because sometimes it's a range. So in books, sometimes they'll say that potassium is negative 90 or negative 95, negative 96. So it's sort of a range. So you don't need to remember the specific number. You just have to remember that sodium, the equilibrium potential for sodium is more positive, and potassium is very negative. Okay, these ions contribute the most to the resting membrane potential. So let's get into the resting membrane potential, what causes it. Okay, so do you guys remember from here, we said that sodium is always moving in and potassium is always moving out. But here we're seeing that sodium is actually moving out and potassium is actually moving in. So it's opposite from, it's moving oppositely, it's moving up the concentration gradient and not down. Okay, when I'm saying up and down, when you move down your concentration gradient, you're following your concentration gradient. So you're going from high to low. When you're going up the concentration gradient, you're moving from low to high. You're moving in an opposite direction. So here we see that both of these ions are moving opposite or up their own personal concentration gradients. This is because this is a sodium-potassium pump. Okay, a pump is something that moves ions up their concentration gradients. It moves them against their concentration gradients. Okay, why do we think we're moving sodium out and potassium in? This is in order for us to maintain this resting membrane potential. Okay, so we're pushing out, you'll notice, 3 sodium ions, and we're pulling in 2 potassium ions. What do you think will happen if we keep continuously doing that? The membrane, because we're pushing out more positive ions than the ones we're taking in. Let's say we run the cycle 2 times, just 2 times. We run the cycle 2 times. We lose 6 positive charges from the cell and gain back 4. So slowly it's becoming more negative because you're losing more positive ions than the ones you're gaining. Okay, so that's the first thing that's contributing to your resting membrane potential. The next thing are your potassium channels. Okay, these are regular potassium channels like the ones we saw here, and they're also contributing to the resting membrane potential. So again, the potassium will move from inwards outwards. So we're going to be losing positive charges at the same time that we're gaining positive charges. So what will that do to the resting membrane potential? Also, it will keep it more negative, okay, because we're losing a lot of those positive charges from within the cell. At the same time, we're going to have also sodium channels, okay? But you'll notice here, and I did this on purpose, there are more, obviously not 3 times more, but there are more potassium channels than there are sodium channels. And do you remember what I said about the permeability of an ion? We said, I can just find the slide. We said the magnitude of current flow is determined by the size of the driving force, sure, and the permeability of the ion, okay? So when we're looking at the resting membrane potential, are we able to tell which ion is more permeable? It's obviously potassium. Okay, potassium is the main ion that contributes to the resting membrane potential because the membrane is most permeable to potassium. Okay, and if it's more permeable to potassium, what happens? Which way do we move the membrane potential? Do we move it towards the potassium potential or towards the sodium potential? Because you'll notice one is too negative, one is very, very negative, and one is very, very positive, right? So the potassium equilibrium potential is very negative, and the sodium equilibrium potential is very positive, okay? If my membrane is more permeable to potassium than it is to sodium, which way will it be pulled? Will it be pulled towards the negative potassium equilibrium potential or up towards the sodium equilibrium potential? It's going to be pulled down. So the membrane is more permeable to potassium. So the resting membrane potential is closer at rest because resting membrane potential is closer to potassium's equilibrium potential. Okay, so it's negative 94. And since it's more permeable to potassium, the membrane, we're going to say that the resting membrane potential is negative. Okay, so it's closer, it's more permeable, sorry, to potassium than it is to sodium. Okay, so more potassium will be leaving than the sodium that's coming in. That will mean that the membrane will develop a negative potential that's closer to potassium's equilibrium potential than it is to sodium's equilibrium potential. And if potassium's is negative 94 and sodium's is positive 61, it will be closer to negative 94. That is why we could say our resting membrane potential is negative 70 millivolts. Okay, again, because it is more permeable to potassium than it is to sodium. So the resting membrane potential is established by the diffusion potentials of permeable ions. Each permeable ion tries to drive the membrane potential towards its equilibrium potential. Ions with the highest permeability will contribute the most to the resting membrane potential. Because the potassium is the most, because the membrane is the most permeable to potassium, potassium will have the greatest effect and will have the greatest contribution towards the resting membrane potential more than sodium. Hope that makes sense. Okay, now from now on, inshallah, it's going to be smooth sailing because, as I said, we're not going to be going too deep into the action potentials since it's going to be discussed in a later lecture. So, excitable cells that can generate an action potential. You guys will learn about what action potential means later on, okay? Action potential basically is when you pass the threshold potential and you're able to basically do contraction or do whatever the cell wants to do. That happens when there's an action potential. So all cells have a resting membrane potential, but only excitable cells can propagate an action potential. Okay. Now, one other thing that they added in your slides for some reason, but I felt the need to go over it, is your channels. So you have ligand gated channels and voltage gated channels. So some channels are only opened after you reach a specific voltage or a specific potential of the membrane. Okay, so channels, the way that they're situated is that they're sort of integral proteins. They are part of your membrane. Okay, so voltage gated channels are gated by the voltage, obviously. So once the membrane potential reaches a specific voltage, that's when they can open or close. Okay, now ligand gated channels are not opened or closed by differences in membrane potential. They're actually opened or closed by hormones or other messengers. So one example is the nicotinic receptors, the ones that are opened by acetylcholine. Okay, so you'll learn later on that acetylcholine can come, and it can basically, once there's so acetylcholine is a neurotransmitter. Okay, once there's a neuronal signal, it will basically send acetylcholine, and it will open up a specific channel, and it'll allow influx of a specific ion. So ligand gated channels are opened or closed by hormones and other messengers, and voltage gated channels are opened by changes in membrane potential. Okay, so I hope that makes sense so far. So we said that the resting membrane potential is around -70 degrees. Okay. Now, let's talk about, if we're talking about a sodium voltage gated channel, a voltage gated channel that's only for sodium. Okay, it's going at -70 degrees, or -70 degrees, at -70 millivolts, which is the resting membrane potential. The activation gates of the sodium voltage gated channel is closed, which is not allowing for ions to diffuse through the membrane. So you have a channel, all right? We're going to be talking about two gates, your activation gates and your inactivation gates. So at the resting membrane potential, your activation gate is closed. So this little thing that you see here labeled in the diagram, it's closed because you're not yet at the threshold, which is what causes your active potential. Okay, so it's closed because it's voltage gated. You're not at the required voltage yet. That's what your threshold potential is. You're not there yet, so your activation gate will stay closed. Okay, now at the same time, your activation gate is closed and your inactivation gate is open. Okay, so at threshold, now the cell will be depolarized. Slightly depolarized means that it will become slightly more positive. Okay, once it becomes slightly more positive and it reaches the threshold potential, the threshold potential, the activation gate will open and it will allow for an influx of sodium ions. Okay, so again, resting membrane potential, which is -70. The activation gate of the sodium voltage gated channel is closed, which will not allow for ions to diffuse through the membrane. And at the same time, your inactivation gate is open. Once you reach threshold potential, okay, which is around -55 millivolts, the activation gate opens and it will allow for an influx of sodium ions. Once that happens, since we said that sodium is positively charged and it's entering a negatively charged membrane or a negatively charged cell, what will happen to the membrane potential? Will it continue to become more positive, or will it become more negative? You're gaining positive ions, so it will continue to become more positive, and that's what your action potential is. Now, for sodium to enter the cell, both the activation and inactivation gates must be open. So I mentioned that the activation gate here is open, and it will stay open once you reach the threshold. At this point, both your activation gate is open and your inactivation gate is open. Okay, and there's an influx of sodium ions. So this is what your action potential is. So during the action potential, sodium ions will enter the cells rapidly. And as you can see here, the red line, if you follow the red line, it started off super negative, right? That's your resting membrane potential. And then it continues to become more positive as you have an influx of sodium ions. Okay. Then you reach around positive 35 millivolts. Okay, that's when your inactivation gate will finally close. So everything we just talked about, your resting membrane potential, the threshold potential, that entire depolarization as sodium ions rush into the cell, your inactivation gate has been opened. Once you reach around positive 35 millivolts, that's when your inactivation gate will finally close. Once the inactivation gate is closed, the membrane again is impermeable to sodium ions. Now, at this point, no more sodium ions can come in. Okay, so we could say that the inactivation gate is closed by depolarization. As you depolarize the cell, which means make it become more positive, as you depolarize it more and more and more, that's when your inactivation gate will close. So inactivation gate is closed by depolarization. Okay. Now, since no more positive charges can enter the cell, okay, and then obviously the membrane is permeable to other ions, the membrane potential will repolarize, meaning it will become more negative. Repolarize, means again, polarize means become more negative, so it becomes negative again. So during the repolarization, the two gates revert to their original position. So now the activation gate will close and the inactivation gate will open again. Okay. Now, if you guys don't understand this concept just yet, again, as I mentioned, that's okay. You'll be taking it in more detail later on. What you could do is you could look up a video on YouTube. You could look up videos. There's a ton of them that show you exactly how the gates, the inactivation and activation gates open and close. Okay, so I do highly recommend watching a video about that just to get the sort of visual aspect of it. So now let's get into just a couple clinical scenarios, okay? Again, not too much. We're going to be talking about it in later detail in other lectures, but just a little taste of it right now so you could get some better understanding. So we said that potassium, since the membrane is most permeable to potassium at resting state, okay, potassium will have the greatest effect and will have the greatest contribution to your action potential. That means that any slight change in your potassium levels outside of the cell will have a very, very large effect on your membrane potential. So in normal kalemia, kalemia, by the way, means potassium. Okay, so kalemia means potassium in the blood. Emia, by the way, is a suffix that means in blood. So normal kalemia, normal potassium in the blood. A supra-threshold, which is an above threshold stimulus, will fire an action potential. That's what we see here. Okay, so any like it's basically everything is moving normally. Any stimulus that's strong enough to, which is super threshold, any stimulus that is strong enough to take the membrane potential to threshold will cause and will fire an action potential. Okay, that's completely normal. That's what we want. Now, hyperkalemia. Hyper means too much. Kalemia, again, potassium in the blood. Too much potassium in the blood. Hyperkalemia depolarizes cells. Okay, so your resting membrane potential should be around negative 70 millivolts. Okay, if you have too much potassium outside of the cell, remember what I said about the whole magnitude thing? Okay, which is that the magnitude of the current flow is based on the size of the driving force, and the permeability to the ion. Okay, so the size of the driving force is what changes here with hyperkalemia. Since you have more potassium outside of the cell, okay, there's a larger concentration gradient, which means that there's a larger driving force. Okay, that means that you will have a greater influx of potassium, and that will mean that your resting membrane potential will be slightly depolarized. Okay, because you have too much potassium outside of the blood, your driving force will increase for potassium, and so will the magnitude of the influx of potassium, which will raise your membrane potential, your resting membrane potential, slightly more positive than it's supposed to be. Okay, now, say that you have a stimulus that in normal situations, in normal kalemia, is not strong enough to take it to threshold. It's not strong enough to take the resting membrane potential to the threshold potential. It's not strong enough. So when you have that stimulus in normal kalemia, nothing will happen, right? An action potential won't happen because you still haven't reached threshold. In hyperkalemia, that same stimulus that in a normal situation wouldn't cause an action potential will cause an action potential in hyperkalemia, and that's because your membrane is already slightly more depolarized than it should be. So in hyperkalemia, increased blood potassium concentration, it will bring the membrane closer to the threshold. Now, a stimulus that would normally be sub-threshold, which means lower than threshold, can trigger an action potential. Okay, that will cause tremors, right? Because your cells are more depolarized. Okay, any small stimulus will cause an action potential, and it could cause cardiac arrhythmias. Okay, you guys don't need to know this right now, but it's just for your better understanding. Now, let's take the opposite scenario: hypokalemia. Hypokalemia, which is decreased blood potassium concentration. it will hyperpolarize. So again, we talked about repolarization, which is making the membrane negative again. But hyper repolarization, meaning making the membrane too negative. Okay, hypokalemia, again, because I said there's too little potassium outside of the blood, it will bring the threshold, it will bring the membrane potential down, and it will cause it to be more negative because there's a smaller driving force that's going to be pushing the potassium ions in. So, so decreased blood potassium concentration. It will hyperpolarize the membrane and make the neuron less likely to fire an action potential in response to a stimulus that would normally be above the threshold. Okay, now in this case, take a stimulus that normally in normal kalemia will lead to an action potential. It's a very strong stimulus. It will take it above threshold. In normal kalemia and also in hyperkalemia, that same stimulus will cause an action potential. But in hypokalemia, you could have that same stimulus that is usually suprathreshold. It's a supra-threshold stimulus that will take the membrane potential to the threshold. But because you have a repolarized membrane, it won't be enough to reach threshold, and thus you won't be able to fire an action potential. Okay, that will cause muscle weakness, among other things, like there's nausea and there's vomiting and all those things that you'll take later on, inshallah. So again, normal kalemia, normal potassium levels outside of the cell in the blood. Okay, so any stimulus that's suprathreshold will cause an action potential. In hyperkalemia, which is increased blood potassium outside of the blood, outside of the cell, it will bring the membrane up closer to the threshold. It will depolarize it slightly, and any stimulus that would normally be subthreshold will cause an action potential. In hypokalemia, you bring the membrane potential down, you'll make it more negative, and in this case, any stimulus that's usually usually supra threshold, any stimulus that's usually strong enough to take that membrane to the threshold level and cause an action potential won't do that, but it won't, because your membrane is more hyper repolarized. Okay, bit of a long one, I know. Let's get into some questions, and then I'll be out of your guys' hair. So the concentration gradient of which of the following ions is primarily responsible for the resting membrane potential of a myelinated nerve cell? Okay, so we talked about calcium, we talked about chloride. Actually, we didn't talk about calcium. We talked about chloride a little bit. We didn't talk about magnesium. We talked about potassium and sodium. Which one? Basically, what they're asking here is which the membrane is the most permeable to which of the following ions. Okay, that's what it means when you have a ion that's very permeable, when you have a membrane that's very permeable to an ion, it will mean that ion will have the greatest effect on the resting membrane potential, or it will be primarily responsible for the resting membrane potential. The answer is obviously potassium, D. Okay, so next question, final question actually. Considering the typical potassium concentration gradient across a neuronal membrane at rest, which of the following correctly describes the potassium flux and potassium conductance? So basically it's asking which way will the potassium move at rest, and how high or how permeable is the membrane to potassium? Okay, so we already said that the membrane is very, very permeable to potassium at rest. That will mean that the potassium conductance is high. Okay, so we could scratch out B, we could scratch out C, we could scratch out E, and we could scratch out F. So we have, it's either A or D. Now, do you guys remember what I said about P's? P's are always moving out, salt is always moving in. So potassium flux at rest is always an efflux. Okay, it's always moving out. So the answer is D, efflux, and the conductance is high. Okay. Now, I hope that this was helpful. I hope I was able to make it a little bit easier on you guys, and that's it for me. And I hope you guys benefited. And thank you.